So today we will be discussing about the regulation of a transformer. In our last class we have derived the expression for efficiency of a transformer. Now apart from efficiency, which is a quality of a transformer, that is better transformer will have higher efficiency. Similarly, apart from efficiency, there is another thing that is called regulation, which will also qualify whether a transformer is good or bad. It is with respect to the maintenance of the constant voltage across the load terminal. That is how good the transformer is. As you change the load across the secondary of the transformer, that the voltage is maintained more or less constant. Okay. Obviously, regulation should be as low as possible for a transformer. And as I told you, regulation or the change of voltage occurs across the load terminals as you change the load because of the internal impedance of the transformer. And remember, it is only the series impedance, that is the equivalent resistance and leakage reactance, which will cause this voltage drop to take place inside the transformer, and in effect the secondary terminal voltage gets affected as you change the loading. So how to derive a handy expression to calculate the regulation of a transformer will be our today's first topic. So for that, what we will do is this: you consider the equivalent circuit of the transformer referred to the secondary side, so that it will be Re2 Xe2, and here is your load terminal. Load terminal, where load is the actual load which is connected, and this voltage we will denote it by V2, terminal voltage V2, and this parallel branch of course will be there in this approximate equivalent circuit, which will often refer. As you can see, the difference of the voltage between this point and this point is no way related by what current is drawn by this magnetizing branch. Difference of this voltage and this voltage will be decided by the drop here. So this parallel branch impedance does not come into the calculation so far as regulation calculation is concerned. And this voltage, what should I write? If V1 is the input voltage, V1 by A. V1 by A. Now, when the transformer is off-loaded, there is no load, under no load condition, what will be the load voltage? That I will denote it by V20. So V20 equal to terminal voltage across secondary with S open, and V20 obviously will be equal to what at that condition? Is equal to V1 by A, because no current flows here. So this voltage and this voltage will be equal. And so V2 is equal to V20 under this condition. And with S open, S closed, let the terminal voltage be V2. Then by definition, regulation is defined as the change in terminal voltage from no load to full load condition, that is V20, the magnitude of this voltage, minus V2, divided by this V20. Now, when you express it in this fashion, it is called the per unit regulation. If you multiply it with 100, you get the percentage regulation. Now, we want to derive an expression for this. So, for that, what we will do is this: we will draw the phasor diagram when the switch is closed. When the switch will be closed, then this current is I2. Suppose the power factor of the load is cosine theta and it is lagging in nature. Then the phasor diagram can be easily drawn as this one. Suppose this is your V2. This is your I2. And this is the load power factor angle theta. Now, to this V2, if you add these two drops, then you will be getting the V1. So, you would add this one, that is, this will be I2 RE2, and then to this you draw a 90-degree angle, and this length will be I2 into XE2. Very simple phasor diagram. And then this will become obviously your V20, which is nothing but V1 by A. Okay. Now, this formula, this modulus means this length minus this length divided by this length. As I told you, across the load you require some specified voltage at a fixed frequency, 50 hertz. That phase displacement with respect to input voltage does not matter, is not. So, magnitude of the voltage is important, whatever you are getting ultimately to the load, because load will only see a source is supplying him, that's all. So, anyway, so we have to calculate. So, this regulation thing, if I apply simple geometry here, suppose this point is A, this point is A, this point say B, then this regulation is nothing but the length OB minus OA over OA. OB divided by OB. You are right. So, this is regulation. Now, we will geometrically try to find out what this difference is, and you will get that formula. That is the idea. Now, to do this, what you do, you have to do some approximation. Suppose you extend this line here and drop a perpendicular from the point B to this horizontal line and call it N. Obviously, this angle is theta because this is parallel to I2, and also this angle will be theta because angle between two straight lines is angle equal to angle between their perpendiculars. So, this is perpendicular to this and this is perpendicular to this. So, this will be theta. Now, this expression, this regulation expression, therefore, regulation, as we have seen, it is OB minus OA by OA, OB, right, and this will be approximately equal to ON minus OA by OB. Because of what? Because this angle is very small. Because RE2, XE2 values are small. So, these lengths are small and therefore, this angle will be small. So, that ON can be considered to be equal to OB. That is, it is BN is an arc of a circle. Is not? If that angle is small, it can be considered to be the sector of a circle. This is an approximation, no doubt. Okay. And this we are allowed to do because of what? Because the resistance and leakage reactance voltage drops are small in a well-designed transformer. So that allows me to approximate OB, ON. So we get this one. Then obviously this ON minus OA is nothing but your AN divided by OB. Now from this point we have to calculate AN then, this length. From this point you drop a perpendicular on AN, that is this one you draw, and call this as M. So your regulation will become AM plus Mn divided by OB. Now look here. AM is equal to what? I2 RE2 cosine theta. Projection of this on this one. So this will be I2 RE2 cosine theta. Then plus Mn. Mn is this length, which is nothing but this length. This equal to this. N is this point. So it will be how much? I2 XC2 sine theta. So I am not replacing Mn by another two names here, straight away writing. Okay. So Mn is nothing but this length, which is equal to I2 XC2 sine theta. Divided by your OB. Okay. So this is an approximate, no doubt, but nonetheless very handy expression for calculation of regulation in a transformer. If you know the transformer is loaded at a power factor of cosine theta and delivering so much of current, then regulation will be this much. You can easily apply. But remember, this calculation does not require, what is the advantage of this approximation? You don't require any phasor addition, subtraction, etc. It straight away gives you the magnitude of the voltage difference. If you know the magnitude, all are magnitudes here, no phase angle. Clear? That should be understood. Now sometimes this one is written in this way. This regulation is written in this way. That is I2 RE2 by this length OB into cosine theta plus of I2 XC2 into OB over OB into sine theta. Now what is OB? OB is the voltage of the secondary terminals under no load condition. Okay, suppose to give you an example, suppose you consider a transformer 100/200 volt, 5 kVA transformer, 50 hertz, single phase. Consider this transformer. You apply to the primary 100 volt rated. Secondary is open circuited. How much voltage you will be getting? 200 volt. Now the transformer is loaded by closing the switch. That terminal voltage magnitude will no longer remain 200 volt. It will change. So what is this OB then for this transformer? 200. That is under no load condition. It will, suppose after loading, it will become 198 volt, 195 volt instead of maintaining 200. Like that. Now what is I2 into RE2 in language? It is the voltage drop taking place in the series resistance of the transformer. taken all the sides together, because RE1 is, RE2 is R2 plus the reflected of R1. So I2 R2, RE2, I2 RE2, the total resistive drop and it is understood we are not referring this resistive drop to core loss resistance component parallel, series, total series resistive drop. Similarly, I2 into Xe2 is the total series leakage reactance drop. Okay, so we can now assign some physical thing associated with this ratio. So this ratio gives me what? It gives you how much of the rated voltage is dropped in the resistance. OB is the rated voltage of the secondary side, is not? How much of it in per unit sense is dropped in the resistance? Similarly, I2 Xe2 by OB will give you how much of the rated voltage is dropped in the reactance. Okay? And this into this I2 RE2 over OB into 100 will give you the percentage voltage drop, only magnitude, percentage voltage drop in the equivalent resistance. Similarly, I2 Xe2 by OB into 100 will give you percentage voltage drop in the equivalent reactance, equivalent leakage reactance. Now suppose somebody calculates, you answer me. I1 RE1 by V1. That is, suppose the resistance is referred to the side 1. He has taken the rated current of side 1 and divided by the rated voltage of side 1. Will this quantity, what will be the relationship between these two? It will be equal. That is the per unit or percentage value from whichever side you calculate, they will be equal. So sometimes instead of telling the resistance and leakage reactance values in ohms and referring to a particular side, sometimes the per unit values will be only specified. Obviously, you can calculate the exact value of the resistance if you wish with respect to a particular side, if you know this relationship with this physical idea. And these are denoted by this letter, epsilon r. And this is epsilon x. So, the percentage regulation formula is sometimes, this approximate formula is sometimes written like this, epsilon r cosine theta plus epsilon x sine theta, where once again remember cosine theta is the load power factor angle and epsilon r, epsilon x are the per unit or percentage resistance and percentage reactance values of the transformer. Now the regulation formula, this approximate regulation formula can be, I will take that issue slightly afterwards. Now this we have done. Now suppose instead of a lagging power factor load, if the load were leading power factor, suppose the load current is leading the terminal voltage by some angle theta, one can once again draw a phasor diagram and derive the expression for regulation with this approximation that OB will be approximately equal to ON, that is perpendicular drawn, etc. But can you predict how this result will change? So this sin theta will become minus then. So in general, regulation formula will be plus minus this one. That I am not deriving. Okay. So you can work it out, and it will be plus minus sin theta. Minus sign corresponds to the leading power factor load. And plus sign corresponds to lagging power factor load. So negative sign corresponds to leading power factor load. Does there exist any load power factor for which regulation will be 0? At what load power factor regulation will become 0? So you can easily calculate. You put regulation 0, tan theta. Will it be a leading power factor load or lagging power factor load? Leading power factor load. See, from no load, whatever is the voltage, with full load at a given power factor, if I want to maintain that voltage, it can occur only at a specified power factor. Otherwise, it will change. But as I have told you earlier also, that the power factor of the load is generally lagging in nature in the power system. Now, if you sketch this one, regulation curve, you will get a curve like this. Suppose this axis is regulation. At say rated current, you are drawing rated current, and this side is power factor. So this point corresponds to, suppose, unity power factor. So there will be some positive regulation, and this side will be lagging power factor, lag, and this side will be leading power factor. And as I told you, for a well-designed transformers, this regulation axis will be about 1%, 2%, plus 3%, like this. I mean, one should not expect a regulation of say 30%, 80%, like that. You should have that idea. Similarly, this side will be minus 1%, minus 2%, like this. Obviously, regulation will be 0, as you predicted correctly, at some leading power factor of the load. At resistive load also, regulation will be positive. So regulation should be as small as possible in a transformer. Now, sometimes a slightly accurate formula is desired. Of course, in almost all the cases, we will apply this formula quickly. Now, I would like to tell you about the efficacy of this formula in order to find out some very important things in this way. See, problem may be of this kind. Once again, refer that transformer, okay, that is 100 volt stroke 200 volt 5 kVA transformer. Suppose on the primary side I have applied 100 volt, and under no load condition I will definitely get here 200 volt. Now the transformer is loaded. One kind of problem will be, which is quite natural to ask, that suppose this load description is known, power factor I know, how much current it is drawing I know, then if I close this one, how much will be the magnitude of the voltage? So I can easily calculate by what formula? Not that straight away regulation formula you can do. You should remember that this OB minus OA is the difference of this voltage. That is I2 RE2 cosine theta plus I2 XE2 sine theta. This itself will be the difference of the voltage. Are you getting? That is this no load voltage V20 minus V2 is this much. Straight, you will quickly calculate and tell this is, therefore V2 will be V20 minus this drop. I am just telling you how to use this formula for some very practical calculations. Perhaps a practicing engineer will be using it. That is, I have applied 100 volt, under no load condition 200 volt. Now I am drawing this much of current from the secondary at a given power factor like this. I would like to know how much will become the magnitude of the secondary terminal voltage. I will calculate this one. Of course, you don't memorize this. What I am trying to tell, you must try to understand this one. This calculation do not involve any phasor calculations. You can quickly calculate some algebraic expression, the magnitude of the difference. And the second kind of problem could be, so the secondary terminal voltage will definitely be different from 200 volt. It may be slightly more if it is a capacitive loading, which is usually not the case, and it could be less than the 200 volt. Now the second problem could be, okay, this is the transformer 100 volt and this is the 200 volt side. I will connect a load and I have to somehow maintain this voltage 200 volt when it is supplied the load at a given power factor. Then the question will be, then how much voltage you have to apply to the primary? The second problem you are understanding, that is the secondary is loaded and at rated voltage somehow that load demands that 200 volt should be there when the secondary is loaded at the terminal of the load or the transformer. So 200 volt I want to get. Then obviously this voltage cannot be 200 volt. Applied voltage you have to play with them. So how much should be my applied voltage? See, now 200 volt, if it is lagging power factor, without doing any calculation I can say this voltage should be slightly higher than 100 volt. Exactly how much voltage then you should apply? Then once again I will apply this formula. You try to understand this point. In that case, what will be the thing? I want to calculate V20. I want to calculate V20. V2 I know. I have specified, known here, plus this one. Are you getting? So this way, this formula is very useful to get this feeling. Perhaps you have to then apply 105 volt in order to have 200 volt at your load terminals. Are you getting? To compensate this one. Now, as we have seen that this regulation should be small, the constancy of the voltage should be maintained. Suppose distribution transformer output, so many users are connected, and it appears from this formula, if one user changes its load, the current on the secondary will change, and hence the voltage will fluctuate, is not? If a major load is changed, suppose in 100 ampere 2 ampere is changed, nothing will be felt. But suppose 100 ampere load transformer secondary is delivering, one major suddenly 50 ampere load is thrown off, switched off, then suddenly voltage will rise. It may affect this one. Okay, are you getting? So regulation by itself, this thing should be very small. Now I will tell you one thing how this can be made small. It can be made small by decreasing the value of RE2 and XE2. If in a transformer RE2 is small, XE2 is small, like that. Now RE2 is small, can be made by using say copper material, which is economical, conductivity is high, because resistance of the winding depends upon rho L by A, is not? So you use copper wire. So there that RE2 to whatever extent you can decrease, you decrease in that way. Now with XE2, whether it can be reduced a bit while designing the transformer. See, so far I have not told you how really a transformer is designed or those aspects, but I thought some basic idea you will understand it better. For example, how XE2 can be reduced at the design level to make it a well-designed transformer, such that those approximations can be brought in, and also the constancy of the load terminal voltage will be somewhat maintained. So the idea is very simple. While drawing so far a transformer, I was drawing like this. Suppose this is the transformer. I was drawing like this. This is the primary winding in one limb and secondary winding on the other limb. Is not? This is how I am drawing. This is the primary, this is the secondary. Now, the leakage reactance, as I told you, is caused by the leakage flux. The flux which only links a particular coil is not a common mutual flux. So between two windings, how leakage flux can be reduced? If they are brought in proximity, then only this leakage flux thing can be reduced. Suppose two coils are separated wide apart in space, then the leakage flux is bound to increase. But if the two coils are brought very closer, leakage flux will decrease. Such simple logic gives us that one. So with that in mind, in a practical transformer, what is done? That instead of allotting a particular limb to a particular coil only, what is done? Suppose the primary winding will be wound. Suppose primary winding turn is 100 turns. So instead of making all 100 turns here, what do you do? 50 turns here and 50 turns there. And of course connect them in series so that it becomes a single coil. And so how will you connect it in series? Suppose the current flows here. Flux is to be produced in the same direction. So how will you connect? This point will be, and these two will be your primary terminals. Are you getting? This is primary, this is also primary. So instead of making the one limb belonging to a particular coil, you break the coil into two halves. This is only primary, and two terminals comes out for supplying. Then where will be the secondary coil? Secondary coil 2 you distribute on the two limbs. That is, primary coil is one. Then on the same limb you have secondary coil. You have secondary coil. Similarly here you have secondary coil. And once again these two can be connected in series with appropriate sense in order to give you two terminals for secondary. Okay, so in the same way this one will be, I don't want to complicate this diagram, looks complicated but not at all, this way. So your two secondary terminals will be this one. this green one is the secondary coil, this one is the primary coil. Now obviously leakage flux will now reduce, because here this on the same core you have got both primary and secondary links. There will be leakage flux, of course, there will be only linking the secondary, but that because of their proximity, closer proximity, that will be certainly reduced. So in a transformer, when windings are wound, it is not that on a single limb you have only single winding primary and other limb secondary, but rather primary and secondary windings will be distributed equally on both the limbs, and they are connected appropriately in series to have your primary and secondary terminals available. So that way leakage reactance is tried to be made smaller and your regulation improved in a transformer. So remember, so far as the rating goes, I will tell you one thing, that in a transformer, I will now come to the rating of the transformer. That suppose a transformer rating is written, nameplate rating is 100 stroke 200 volt stroke 50 hertz and suppose 5 kVA transformer. You immediately come to know what is the rated current of this side, LV side, what is the rated current of that side, and the frequency, rated frequency you have to apply, 50 hertz. Now I will ask you, suppose you apply, instead of, you apply 100 volt to the primary winding, 100 volt to the primary winding. Suppose this design transformer is this. If I apply 100 volt, 100 hertz, what do you expect at the secondary? Suppose open circuit. Voltage induced RMS voltage magnitude will be 200. Is not? RMS voltage magnitude does not depend upon frequency. Secondary induced voltage frequency will be 100 hertz. Are you getting? It will be 200 volt, 100 hertz, like that. Then you will perhaps load it like that. So what I am trying to tell, a transformer which is designed for 50 hertz, suppose you give voltage, you maintain same RMS voltages of the respective side, but you suppose apply 100 hertz. You will be getting here 200 volt, 100 hertz, like that. But in which way the performance of the transformer will get affected? Will it become better performance? Definitely not, because with this frequency your core loss may increase, because f square it depends, because 100 hertz means your flux density also decreases. For a same voltage, is not, B depends on V by F. So frequency is increased, this one increased, but core loss also depends on frequency squared. That will increase, and also the leakage impedance drop of the transformer, XC2, etc., will become higher. So regulation of the transformer will become poorer, and so on. So anyway, what I am trying to tell, obviously a 50 hertz transformer should not be operated at 100 hertz. That is also not required, because in our country it is 50 hertz design. But as you know, frequency may slightly change this way, that way. It is not also constant, 49 hertz, 48 hertz, like that. So anyway, around 50 hertz its operation will be there. But my next question will be, suppose this transformer, 100 volt, 200 volt transformer, suppose I will energize the primary with 100 volt, 25 hertz, lower frequencies, suppose I will energize. What will be the secondary voltage and its frequency? 200 volt, 25 hertz, at least theoretically it should be like that. But the important point is, at low frequency, if you give supply, something else will also happen. That point I want to highlight whatever time is left today. Why it is so? You remember that if you operate the transformer at a reduced frequency, what will be the level of flux with respect to the rated condition? Suppose with 50 hertz 100 volts applied, whatever is the flux developed inside the core of the transformer, that let me call it rated flux. Now if I apply 100 volt 25 hertz, that flux level has to be how much? 4 times. Only 2 times. It will become double, because V by F decides the flux level. Flux level in the transformer is decided by proportional to applied voltage by frequency. Applied voltage I am keeping constant, magnitude of the RMS voltage. If you reduce the frequency by half, flux level will become double in the core. Now in a transformer, so how much will be the magnetizing current? That becomes the crucial point. See, in a transformer, a practical core material, whatever is used, the BH curve of the material, it is not straight line, goes to infinity. It is like this. This point is very important to note. Suppose the BH curve of the material is somewhat like this. It will have some saturation. This is H, this is B, this is B. And when the transformer is designed, it is designed at the what is called knee point in order to reduce the size of the transformer, etc. You should have in the just after the linear portion at the knee point the transformer is designed. That is, this is the B rated of the transformer. Because core area etc. are constant, so this axis can be also treated as flux level. You understand? So suppose this is the rated condition, and this much will be the magnetizing current of the transformer. Okay, 50 hertz operation. This is the rated flux condition. Now the moment you apply 100 volt 25 hertz to the primary of the transformer, because KVL equation is to be satisfied in the primary, that's why flux level has to be twice. But how much current will be needed to establish that flux inside the core of the machine? That how shall I find out? This 2 times of this into this. And how much current it will take? You now draw a line here, and this one you extend. So wherever it will cut, that will decide the current. And what I am trying to tell, that current may exceed many times than your rated current of the transformer. See, in the low frequency operation, one should be very careful about the operation of the transformer, because the magnetizing current that it will draw from the supply will be quite high, because the initial operating point corresponding to rated condition, it is generally done here at the knee point. Suppose a transformer is designed at this level, then of course if you reduce the frequency, magnetizing current will become twice, like that I can say. But that twice thing does not hold good because of the bend in the BH curve of the material. Okay, so at lower frequency of operation with same voltage, you cannot do it. However, at lower frequency you can operate it. Then what voltage you should apply? Such that, so you then apply 50 volt 25 hertz. You can use this transformer, but apply to the 100 volt side 50 volt 25 hertz. It will act as a transformer, but on the secondary you will be getting 100 volt 25 hertz. Are you getting? Then the flux level in the core will remain same. So we will see also this is true in case of an induction motor, that if you want to control the speed of the machine, frequency is controlled in the lower range, then you have to reduce also the supply voltage with the same ratio in order that flux level remains constant. Magnetizing current drawn from the source remains constant. Are you getting? Now I will not derive this, I will ask you to get a further accurate result of the regulation of the transformer by doing like this. I will give you highlight next time if you cannot do. That is another approximation of this one can be done in this way. Instead of making the approximation at this level, what you do, you draw an arc here. Called this point Q. Okay. Then calculate regulation, that is OB minus OA by OB. So for OB I write OQ minus OA by OB I write. This is no approximation. OB equal to OQ. I draw an arc with O as center. Okay. Then OQ minus OA, as you can see, it is equal to AN plus NQ divided by OB. This NQ you now try to estimate in a better way. AN is this one, we have already calculated. This thing is known. How this NQ can be now, slightly better way estimated. That can be done by this right angle triangle. From this right angle triangle, you know that BN square is equal to OB square minus of ON squared. So in this way, try to find out whether you can get another additional term and get an further better results of regulation. Of course, for all practical purposes, we will be happy to use this regulation formula. And another thing I want to remind you that while giving a problem, don't start making phasor sum here and get V10. Try to exploit this simple equation to get those readings. That is, you will be often tempted, let V20 something magnitude angle, why not add these two drops like that? But this may, you will arrive at the same results, but after so many calculations. Are you getting? More accurate result will be what? V20 plus I2 bar Z2 bar. You get V1. Anyway, next time we will